Alright, and now it's time for an example where we go through and classify the extrema of a certain function which is given to us, and wear your patient pants with these problems because if you remember, these do take quite a while. Okay, so we're going to begin as we would in the single variable case by finding critical points, and so we might remember that in what we said for critical points was we need to look at the derivative matrix. But here, since we have one-dimensional output, we can actually just look at the gradient. And if we do this, I believe we get 3x squared plus 2xy, comma, and then x squared minus 2y minus 4. Okay, and if I play around with this just a little bit, let's see, I end up being able to write this as x times 3x plus 2y, and then comma, x squared minus 2y minus 4. And again, for critical points, I'm trying to find when this is 0, 0. Okay, and so what I can see is that, well, if I want 0, 0, one way I can get that is by saying x is equal to 0. Okay, and so then if I say x is equal to 0, that sort of forces in that second component to have 0 squared minus 2y minus 4 is equal to 0. And, well, then I believe I just get y is equal to minus 2. Okay, so I have critical point 1 as 0, comma, minus 2. Alright, and then in the second case, well, that's where I have to say, well, this other thing could be 0, so let's say 3x plus 2y is equal to 0, and if I solve for y, I believe I get minus 3 halves x, or minus 3 halves x, okay, and then plugging that into the second component, I have x squared minus, and then after I do the math there, I believe I just get plus 3x minus 4 is equal to 0. Well, okay, factoring, and I get x plus 4, x minus 1 is equal to 0, and so then I get the critical points, 1 in the x component and minus 4 in the x component, and then solving these I get minus 3 halves and then 6. Okay, so I have 3 critical points. Alrighty, so then I have my critical points. Now I need to classify them, right? So I need to, according to the second derivative test, look at that Hessian. Okay, so it'd probably be wise to actually find the Hessian first. Oops, let's go down here and we're going to find the Hessian. And I need to refer to my gradient. Okay, and so Hessian here is going to be 6x plus 2y, and then in the off diagonals I just get 2x, and then in the fyy I believe I just get minus 2. Okay, so then when I look at the Hessian for my first critical point, okay, so let's look at Hessian of f at 0, comma, minus 2. Alright, what I end up getting is negative 4, and then 0, 0 in the off diagonals, and then minus 2. So then I look at my sequence of determinants. Oops. So I get negative. Oops, and why didn't that copy? Oh, maybe I deleted it. Oh, well. Okay, so I get a negative and then a positive, right? So I get negative and then positive. Okay, so this one is going to be negative definite. Okay, and if you recall, negative definite is going to actually produce a local max. Okay, Then, so I've classified one. Let's go on to another. H of f at 1 comma minus 3 halves is equal to. Okay, and then calculating, I get 3, and then 2 in the off diagonals, and then minus 2. So then I get positive and negative. Okay, and so this is going to be indefinite. And then this is going to be a saddle. Okay, and for my last one, hf of negative 4 comma 6 is equal to, okay, do the calculation, negative 12, negative 8, and negative 2. So then I get negative and negative. I'll let you confirm. And so then this is also indefinite, which gives me a saddle. Okay, and so that's kind of the idea. What I would encourage you to do is graph it, and maybe in CalcPlot 3D, and look and find these points and verify that they actually are local mins, and saddles.